Welcome to P6, take 2. If you're in the classroom, you know why it's take 2, and you can chuckle about it later. Right, for now, we're going to do P6, radioactivity. And we're going to cover some of the key points about radioactivity. We're going to talk about radiation types. So make sure the notes you have all of the, you don't have to do this again from scratch, you could just be adding on. We're going to talk about what background radiation is. Whilst you're copying this down, what is background radiation? Anyone? Shout out.
Stuff in the background.
Stuff in the background, yeah. And someone was saying stuff from where? Natural, yeah. There's natural background radiation, which would suggest there's also what? What's the opposite of natural?
Unnatural.
Which is otherwise known as man-made. Yep. We're going to look at the atomic model. So I'll add those in, as because we've done them now. We've got natural. And we've got man-made. Now already this is quite wordy, but I'll try and go to diagrams as soon as I possibly can. We're going to talk about half-life. So I'm going to draw this diagram over here and ask you guys to explain to me what it means. We're going to look at medicine, because there's a medical component to radiation. We're going to look at fission, and I'll put over here fusion. Okay.
What's the bottom one there?
Fission, F-I-S-S-I-O-N, fission. Okay, so we're already got it's actually a pretty big topic, P6, and we are simplifying it down a little bit doing it this way, but it will be useful to us long term. So radiation types, let's go back over to the right hand side even. What are our 3 types of radiation that we deal with? Anyone give me any of them? I don't care what order I get them in. Gamma. I was going to take one, so it might give you all a hint what I'm looking for. Gamma. First letter in the Greek alphabet. Alpha.
And B.
And the second letter in the alphabet. Yep. Beta. Well done if you had those. So they've come from the classroom. Alpha, beta, and gamma. They all have symbols. You should probably know what the symbols are. Alpha looks a little bit like a fish. Beta has a long tail. And gamma looks effectively like a Y. Alright, that's not going to be quizzed or tested on, just should know it. Right, so what are the key things we need to know about alpha, beta, and gamma? Someone want to get me started? What do you know about them? I don't mind which one, just tell me which one you're talking about when you tell me. You know anything about alpha, beta, or gamma? It's fine. You're allowed to shake your head. This is your opportunity to write loads down. Next time around, you take the information away and you're starting to store it. Alpha, beta, or gamma? Give me one.
Alpha has 2 neutrons.
Okay, alpha has 2 neutrons, 2 protons. Okay, so I'm just going to write 2n plus 2p. What am I straight away doing? I'm forcing myself to remember what n and p stand for. 2 neutrons, 2 protons. How many electrons does it have? Come on, I want to write it down. None. Doesn't have any electrons. It's a trap. Why would I set you up for that trap? Because I'm mean and nasty. No, because it's a common question. If it has no electrons, what does it want? It wants electrons. Absolutely. What's it going to do? It meets an atom that has electrons. Steal them. What do we call that process? Come on, a bit of chemistry creeping in here. Starts with an I. Close, but not ionic bonding. Ionization. Well done. So it is highly ionizing. Okay, I'm just going to add that in, but you should know highly ionizing means it wants to take electrons out of everything. In fact, alpha particles will strip electrons off an oxygen atom. Okay, we do that with the spark generator in class. So all those little sparks you're seeing, okay? That's all right. So you see those little sparks of the spark generator, that's the oxygen atoms trying to get their electrons back from somewhere else because the alpha particles come along and just taken them. stolen away. Right, something about beta particles then. What is a beta particle? Because if you can understand what a beta particle is, it does help understand some things about it. Alpha particle is the biggest or smallest? Biggest. So we need something smaller that's in the atomic model. What's smaller than a neutron and proton? It's the only three things to choose from. Electrons. A beta particle is an electron, but it's doing something different to normal electrons. The electrons that travel around the wires up above you right now, they move about 5 millimeters a second. Tiny. They're barely moving. And in fact, they're just going backwards and forwards lots. Barely moving. So what might the electron in a beta particle be doing? Going how fast? Do you know? Not quite. It can come out of the nucleus. It comes out as a decay chain between a proton becoming neutron and neutron becoming proton. So electron is ejected from the nucleus. Doesn't want to be there. So it's an electron and it's high speed. Okay? So it is an electron, just like you know now. It's just moving very, very fast. So one of the things that irritates me when people say electrical, when we're doing P10 electrics, the electrons must be moving really fast. No, that would be bad. If they were all racing around, we'd be exposed to beta radiation all the time. Okay, they're actually going very slowly. High speed, that tells us some of the characteristics about them. They're very small, so how ionizing do you think they'll be? More or less than an alpha particle? Because size matters here. Less. They're still ionizing, but just less. So we'll just we won't put a little arrow, we'll just do less ionizing. And we're just comparing that to alpha particles here. Less, that should be ionizing. Less ionizing. Still, I don't want to be hit by beta particles, but if I have my choice, I take a beta particle over an alpha. There is, notice I cleverly snuck in there my little E minus. What if I do this? E plus. You can't have a positively charged electron. No, it's just singular. We're treating it as a singular. Good guess though. Somebody tell me about that electron. It's got the coolest name in physics. A positron. How is that not the coolest name in physics? A positron. Now a positron is literally a positively charged electron. There's no difference between the two except for how they're formed. Okay, so when they come out of the nucleus, so you're quite right in saying they both come out of the nucleus. One comes out as a negatively charged, one comes out as a positively charged. We're going to go look at that in a little bit more detail later on. Actually, we won't do, we'll just do some practice questions, but I'll mention that at the time. Gamma. Somebody tell me something very, very important about gamma if I was comparing it to alpha and beta. You've already had one, go on.
The charge doesn't change?
Interesting. There isn't any charge. But there's a reason why there's no charge. Go on then. It is a wave. Okay? It's part of, and I'll go a little bit further, it's part of the electromagnetic spectrum. It's an electromagnetic wave. There is no particle. Now notice I'm getting very wordy here. So this would be my starting point for any sort of P6 revision note. Okay, so if you're already getting most of this information, I would suspect or suggest even that you should try and cut this down to a few key points, not as wordy as we're making it.
What does that say in brackets?
No particle. Sorry, I dropped the pen halfway through writing particle. It doesn't even look like a word at the moment. No particle, which is important. It is, so if it's not even a particle, ionizing, yes. More or less than an alpha particle?
Less.
Way less, way less. Still ionizing. Even, I'll put even less ionizing, even less. Notice I'm sort of measuring everything against one thing. They're all ionizing, they're all dangerous in their own right. Now, here's the big difference. We talk about ionizing first, as if it's the only thing that matters. Alpha particle, most dangerous. I would not want to eat or ingest, breathe in an alpha particle. Okay, that would be unhealthy for me, and I wouldn't want. I'd do everything I could to avoid it. Why would I not be afraid of alpha particles? There's something about them. Go on then.
They can be deflected and reflected
Oh, you were on the right track. It wasn't even lead. Think something even more common right in front of you. What are you writing on?
Oh, paper.
Paper. Alpha particles so big it won't go through paper. Won't go through skin. So I could put, not that I would try this, an alpha particle on my arm. And it shouldn't hurt me. I'm not going to do that to find out the hard way. But the alpha particles don't penetrate through skin or paper. Still don't want to eat or ingest them. Okay, that's pretty obvious. So somehow I need to squeeze in up here. Least penetrating is the word we use, because that applies more to the other two. What they'll pass through penetrating is what we're talking about. Now, our high-speed electrons are moving quick. They will pass straight through us. But think of because an electron is quite small, excuse me, it's traveling really fast. As it meets a material, the material's like a baseball glove, and it's just going to catch it. Okay, it's going to absorb the energy from the electron. It's not going to stop it being an electron. It's just going to slow it down. It's like if I threw an egg at you. Rosie, if I threw an egg at you, how would you catch it? And what would happen if the egg hit your hand like that?
Smash.
Smash. So how would you catch it if you didn't want it to smash? And what would you do with your arms? You'd try and take it in, right? Just like a netball, so you don't break your fingers. Excuse me. Drink water, start coughing. So it's the same idea with a fast-moving electron. You need to absorb that energy. And the things we put down on the sheet here, we'll put down it's slowed down by. Notice I didn't say stopped by. Slowed down by. We normally talk about aluminium. It's one of the most effective materials. That's meant to say aluminium, but I have clearly run out of space. And you don't need much aluminium. 1 centimeter will stop most of the beta particles. They usually say 1 to 3 centimeters. Okay. Stay with us. Right, the last one. Gamma, it's the least ionizing, but the most penetrating. So right now, there is a source up in the radioactive safe that is emitting gamma particles. Some of them will reach this room. Okay, very few. That's what makes it safe. There's gamma radiation coming from the sun right now. There's a lot more coming from the sun than there is coming from that safe. So we don't talk about it as being highly ionizing, but it will penetrate through lots. So there's two things we talk about stopping, which is a bad word, absorbing the energy from gamma radiation. What are the two things that we use? You had one earlier. Lead. And anyone know what the other one is? Go for it. Concrete. So we usually talk about 1 inch of lead, which is terrible. That's imperial. So it's about 2.5 centimeters of lead. It's quite a lot. It's heavy. Or 1 meter of concrete. Okay. So most penetrating is gamma. And we talk about 2.5 centimeters of lead or 1 meter of concrete. Now that isn't actually going to stop all of the gamma rays. It's just going to get to a point where very, very few of them get through. Okay. What is all of that information that I've done on the right hand side there? What does that look like it's setting you up for? What kind of question? Is it going to be a 1 marker?
No.
What kind of question? 3 parts.
3 more.
Think bigger than a 3 marker. 6. Okay. Classic 6 mark question. 3 parts, alpha, beta and gamma. What are you going to talk about? What 3 parts are you going to talk about?
Alpha.
Beta and gamma. It's set up for you. It's just like that. Okay, you just need to know the key parts of each one. Okay, there's a lot of information there. There's a lot of information in your books at home. You've got to get it out of the books, summarize, and in a way that you can remember it. Everyone all right with that? They're all nodding. Good. That's more for the video than anyone else. Right. Let's talk about the atomic model because it's very important that we do, and we have actually already talked about a lot of this already. So let me draw that, because I'm going to use this later on as well. What am I drawing? Anyone? I'm drawing an atom, aren't I? How many shells does this atom have? Anyone tell me what it is? Anyone tell me what kind of atom it is? I'll give you a hint. It's got the same number of protons as it does electrons. How many electrons does it have?
4, 6.
I hope it has 6, otherwise I can't count either. 6. 6 protons. What's got 6 protons? Oh, come on, this is a really important one, guys. It's the only one I ever kind of harp on a lot about. We use it for half-life. Carbon. Good. So this is meant to be carbon. So I don't get any points for my lack of drawing ability, but that's okay. Carbon. And this is going to be a particular type of carbon, because we're going to talk about half-life in a second. This is carbon 14. If I put a number after it, what am I talking about? Have I changed the number of protons? What happens if I change the number of protons? Is it still carbon?
Yeah.
No.
Head goes the other way. That way. No. It's no longer carbon. If I add another proton to it, it's going to have 7 protons, so its atomic number will be 7. Anyone know what that is? You're breathing a lot of it in right now.
Oxygen.
No, that's 8. No, that's only about 1% of what you breathe in. Nitrogen. Nitrogen's 7, oxygen's 8. You don't need to know that for GCSE, but it gives you an idea of how these all relate to each other. So carbon 14. So if I haven't changed the number of protons, I've obviously changed the number of... What else is in the center of the... What's in the center of the atom? Nucleus. Okay, we're going to add that. So nucleus. I'm going to add the word nucleus in. Now I know we have to. Nucleus. We now have our nucleus is made up of protons and neutrons. That's all I'm going to write for that. And there are an extra 2 neutrons in there. So normal carbon, which makes up about 99% of all carbon, is 6 neutrons, 6 protons, 6 electrons. 6, 6 and 6. Really easy to remember. It's also the one we use to measure all the others. So we base our measurement on everything else in the world on carbon 12. Carbon 14 is a bit different. It has 2 extra neutrons. It's also radioactive. Does that mean it's dangerous and going to kill you? I probably gave it away by my tone. No. Guess what? You've all got carbon 14 in you right now. Dun dun dun! More for the people at home. Carbon 14 in you right now. Hang on, but it's radioactive. Yes. And right now, if you were to die and I was to take this entire class and bury you in the field... Oh, this sounds terrible when I'm recording. I really shouldn't make this joke. Let's imagine a terrible incident occurred and a volcano covered us all in ash. See, I've changed it already. And they found us in about 20,000 years. At the point we died today, I know it's a terrible story, we all got killed by a volcano in Sevenoaks. What are the chances? At this point, we all have a certain amount of carbon 14 in us, but it's radioactive. So in 20,000 years' time, that carbon 14 would still be in us, but it would have decayed down. Okay, it would be less and less and less carbon 14 left in us. So this curve over here is meant to summarize. That's 100%. That's today. Okay, in 5,730 years time, I'll talk about that number in a second, don't panic, we would have 50% of the amount of carbon 14 we have as right now. And another 5,730 years after that, we would have 25%. Okay, so you end up with a nice exponential curve. Now I haven't drawn it brilliantly, but it shows the point. Our half-life formula is 1/2 to the power of n. The n is our number of half-lives. Now, I said that number 5,730. They will tell you that in an exam. You don't have to remember that number, okay? They might even just say 5,700. All you're looking for, if they mention 5,700, they're talking about 1 half-life has occurred. So after 5,700 years, we would find half the amount of carbon 14 left in us. Another 5,730 years, it'd be a quarter, and so on, until eventually you get to a point where there's so little. This is how we know when we dig something up that was alive, something biological. We can measure how much carbon 14 is left in it and tell you when it died. So if we did all get crushed by a killer volcano today, and they found us all in 20,000 years, there might have been 10 volcanoes between now and then. It's just a really bad place for volcanoes. They won't know which volcano we were killed by, so they would carbon date us. And they say, they've got roughly, what's that, 20,000 years, so maybe 4 half-lives have occurred worth of carbon-14, so they can tell roughly when we died. It's not super accurate, but it's pretty good to tell whether, if you dig up some human bones outside in the garden, whether they've been there for 200 years or someone buried them a few months ago. That's different. Okay, so that's not obvious. Henry's looking at me like, is that a problem? Yes. That's the difference between archaeology and murder. 2 different fields. Right. All the jokes aside now. So let me ask you a half-life question. How much, let's do 30, so I'll do a half-life for carbon-14. I'll write the number up for you, 5,730. Let's say we take a sample of some bones. We find some bones and we find they have 1/16 of carbon-14 in them. How long have the bones been there for? 1/16. Slow down. So what you need to do is work out what 2 to the power of n equals 16. What does n need to be to make it 16? So 2 to the power of what equals 16? Rattle, just go through the numbers if you can't do this otherwise. Just do it in your head. What's 2 to the power of 1? 2. What's 2 to the power of 2?
4.
What's 2 to the power of 3? Put in your calculator if you have to.
8.
It is 8. 2 times 2 times 2 is 8. 2 to the power of 4?
16.
16. I can't do this with my left hand. How many half-lives have occurred?
4.
4. How many years in a half-life? I'm pointing at my screen. I'll put it at the board. That times that tells you how old it is. So for the people at home, we have just done what's 1/16. It's 1 to the power. So this would be the same as 1 to the power of 4. So we take that number 4 and we times that by 5,730. And someone with a calculator is going to tell me it's about 23,000 something. What is it, sorry? 22,920. Okay, I've got to be accurate because there'll be people at home who will write in with emails if I get this wrong. Okay, so it's very important. Is that right? 22,920?
Yeah.
Okay, so that's how we would work it out. So they take a sample and say there's 1/16 of the carbon-14 left. That means it's roughly 23,000 years old. Sound simple? Okay. How much carbon would I find then if I was digging up bones that were 42,000 years old? Step 1, what are we going to do? Talk me through it. Divide it by 5,730. What's that going to give us? Number of what? Good, number of half-lives. So let's divide 42,000. Oh, I can't draw, I'm too close to the bottom. 42,000 by 5,730. Somebody tell me how many half-lives that is, please.
7.
Go on. Let's put it in the calculator. Let's get it out.
What is it?
42,000 divided by 5,730. You done already?
Yeah. 7.
Go on. I'm not letting you off the hook. Come on. It's only because you haven't got your calculator up. Everyone should be trying this because the next bit's the hardest bit.
It's like a 7 point loads of numbers.
Roughly, just give me this short version.
7.33.
7.33. Concur?
Yeah.
Yep, good. 7.33. We'll use that. So 7.33 half-lives have occurred. Great. That's not the question that we got asked, was it? What was the question I asked you?
How many carbon?
How much carbon-14 would be left, right? So now we need to put that into our half-life formula. So our half-life formula is 1 over 2 to the power of n. So I want you to put in the place of n, 7.33. Start off by using the fraction button on your calculator. Okay, it makes life easier for you. 1, and there's a button on your calculator. You can put 2 to the power of, there's a little box depending on which calculator you have, and then you can put 7.33 in there. Make sure it looks like this before you press equals.
What, 2 to the power of what?
7.33. What do we get?
6.2.
Oh, we got standard form. Okay, 6 point. Just give me the first two. 2, 1 times 10 to the power of minus 3. Good.
Wouldn't it be 2, 2 because you round it up?
Okay, yep, we've got a rounding question. Fine. I'll leave that to whoever's doing this at home or you guys now. So how do we turn that into a percentage? It's a decimal at the moment, isn't it? How do we turn that into percentage? Times it by what? Times anything by 100 will give you a percentage. So we times that by 100. So I can tell roughly it's going to be to the minus 1. So it's going to be 0.621%. Is that right?
Yeah.
Yep. Okay. So there's not a lot of carbon-14 left at that stage, is there? So the instruments they use to do this are very, very sensitive. Okay. Indeed, yes. To give you some idea, they can carbon date anything with relative accuracy from about now until about 90,000 years old. Beyond that, there's a few other things they have to do to get super accurate. So, anyone heard of Lucy?
Oh yeah.
Yeah. How old's Lucy? You do this in biology, I imagine. I've actually met Lucy. I actually went and saw her. She's in a museum in Germany. Who's Lucy? I'll give you a hint. She's in a museum, so she's not alive. Lucy's 2.4 million, or I always get this wrong. I think it's 2.5 million years ago. Lucy's pretty much at the point that we stopped being something else and we became Homo sapiens. Okay, we started being humans. Okay, she was pretty much the transition. So she has all the characteristics of an animal that walked on 2 feet.
A monkey.
Monkeys don't walk on their 2 feet. They can, but they tend to use all 4 limbs. So their nails are always ground down. So Lucy also showed that she was using tools. So when they found her, they found tools. So she was digging.
I don't know if she's called Lucy.
Like, her name is Lucy because they named her.
They find out her name and they named her. It's just a bit strange to call her Lucy.
For the benefit of those at home, there is an ongoing conversation about how they named her. Not anything useful about her, how they named her. Right, moving on rapidly before we lose complete control of the classroom. Right, shh, guys, back with me, please. There's a few things left on the board that we haven't covered yet. Medicine. Okay. Common trap to get caught up in is you start talking about things that are medical, yes, but not radioactivity. Ultrasound. What's ultrasound?
Babies.
Yeah, used for scanning babies, not just babies, but scanning in general. They'll scan spleens, livers with ultrasound. So not just for pregnant women, but what is it? Is it radioactive?
No.
Definitely not. Is it part of the electromagnetic spectrum?
Yeah.
No.
There it is.
Yes.
100% no.
No, I think I gave it away in my face. No. So ultra sound.
Sound.
It's a sound wave. So what type of wave is a sound wave? We've just gone across P4, 5 and 6 with one question, by the way. This is as complicated as I could probably make it. No. Two types of main waves that we deal with. Most of the light waves are, well, all of the light waves are what kind of waves? Starts with T. Transverse. Well done. These are videos you want to watch tonight, guys. I'll try and upload them tonight or tomorrow before you do your physics quiz, okay? Because this is important stuff. They're transverse waves. Sound waves are the other type. Start with an L. Not you. You've already got it. Breaking eye contact. Caught you. Starts with an L. No. No, not linear. Long.
Longevity.
No, but it does start with the right word. Longitudinal. I was looking for. So, hold on. Shh. straight away we've dealt with misconception. Ultrasound is not medical imaging using radioactivity. Okay? Is X-ray?
Yeah.
Yeah.
Are X-rays radioactive?
Yeah. Because don't you got that weird like thing on you?
Yeah, it is, because the doctors have to sprint out of the room.
So which one's alpha? So X-rays, is it alpha, beta, or gamma? All right, I'll ask you a different way. Hold on, let me put it up here. RMIV. There you go. What have I just drawn on the board? What do the letters stand for? Anyone? Radio, microwave. So these are all part of electromagnetic spectrum. Notice something about gamma and X-ray. Are they the same thing?
No, they're different.
They're different. So X-rays are not radioactive. However, they are ionizing. So in the same way that radioactive alpha, beta and gamma will ionize you, so will an X-ray. But an X-ray is just a wave of light. Okay, it doesn't have a particle. Okay, so this is where we've got to be very, I said we had to be very careful. We just dealt with two massive misconceptions in a row. So with medicine, we are almost totally dealing with gamma.
What about when they treat cancer? Is that correct?
Good, I'm glad you asked that question. The question was, what about when they're treating cancer? The P5 video that I've just made with the other class, I went into quite a bit of detail about that. We're a little time sensitive, so we might come back to it if we've got time. But have a look at that video and we'll go into quite some detail about how gamma is used. All right. Medicine, anything else used radioactivity wise? So we still use beta tracers. So you might eat a biscuit that's got a beta particle attached to it. You might have a potassium part to it, and it'll attach to the end of broken bones in your body. So they can then take an X-ray of you, and it looks like taking a photo of from an aeroplane at night, and you see lights, all the street lights lit up. Okay, so you can see all the little bits of radioactivity where the little bits of broken bone are. So that's more with people with stress fractures or ligament damage, because those little bits of calcium will attach to the end. Okay, it doesn't last very long, 4 or 5 hours, and it's all out of your system. So they actually have to make it at the hospital because it doesn't last very long. You eat the biscuit, they take the image, job's done. My son, when he was 7 months old, had not a biscuit because he was too young, had an orange juice with it in there because they were imaging his kidneys. So while he had the orange juice, they literally put him on a live scanner, and they could see the orange juice, which wasn't orange juice at that stage, it was just the radioactivity, going through his kidneys, and see exactly how his kidneys were functioning. So very useful, because otherwise how would you know how the kidney was working? Okay, so there is some really clever things they do with radioactivity, but of course it's all very low level stuff that's not going to damage you. So 4 or 5 hours after that image was taken, there'd be nothing left inside of it. It would have all decayed to nothing, all right, or just been passed out. Right, the last two that we need to get onto, hiding down here, both very big ones. Fission and fusion. What have they got in common? Why would we do either of these two? They sound similar. They both start with the letter F. Yeah, I'll give you that. Think Simpsons. What's Simpsons? Fusion or fission, do we know? Anyone want to guess? 50-50 guess.
The yellow people.
What, sorry?
The yellow people.
The yellow people, yes. No, that's not what I was going for. Okay, so, thank you. This is our power plants. I'll put power plants up here. Nuclear fission is our power plants. What they both have in common is energy released. Okay? So, Henry, you need to pay attention because my writing's getting a bit messy here. Energy released, they both have in common. What they differ is that fusion is combining. Fission is splitting. Okay, so let's start with fission very quickly. We take a very big unstable atom. In fact, we make it more unstable. We take nuclear 235, uranium 235. Okay, so it has 235 neutrons and protons. It has 92 protons to start with, so it's got lots and lots of neutrons. It's very radioactive. It doesn't like being on its own. It likes to break down, but we make it more unstable. We actually fire a neutron into it, and for a very brief period of time it becomes uranium-236. Uranium-236 doesn't work. It doesn't lock together. It becomes unstable, so unstable, with so much energy, it actually splits into two. Now all the forces that would hold it all together are no longer required. It's now split in two. It's now far more stable. So what happens to all those forces? They're all energy to start with, to be fair. What happens to all that energy if it's no longer required?
Oh, is that the
It emits it.
atomic bomb?
Yeah, that's an atomic bomb. Okay? Or in a nuclear power plant, what we do is that is actual reaction, but we slow it down. So we only allow that to happen at a certain rate. If we let it go, the nuclear power plant would explode and blow up. Okay? So this is all about splitting of atoms. So it's all about making it. Now I would have made you, if you're in my class, I would have made you draw the diagram of a splitting atom with all the key parts to it. Now if you're not in my class and don't have the diagram, Google uranium-235 splitting and you'll find many diagrams online. I would get one without any information on it and see whether you can fill in what's going on. And if you can't, have a look at the ones with more information on it and put the picture together. Okay? But come and find me when we start doing intervention sessions later if you want more details on that. Nuclear fusion is the other one. This is a bit different. Nuclear fusion is actually combining atoms. So if I've got, and I like to start off with my analogy of two magnets. I've got two magnets and I get the north and the north. What happens as I try and push them together? Do they want to go together? No, they actually actively repel. Imagine if they suddenly didn't need to repel. Imagine all that energy it took to get them together was suddenly not needed. Where would it go? So I've got this huge amount of energy forcing them together, and they no longer need to be forced together. The energy would go out. Okay, that's nuclear fusion. The reason why they suddenly don't need to be forced apart is if you push two protons hard enough together, and we're talking about lots of temperature, lots of pressure, so this typically happens on the sun, happens all the time on the sun, that's what's going on in the sun. One of those protons, which are made up of quarks, which are subatomic particles, not in GCSE, you don't need to know much about this. If you do A level, you'll learn all about quarks. The quarks inside a proton, you've got two ups and a down, and in a neutron you've got two downs and an up. Basically, we can grab one of those quarks, we don't grab one of those quarks changes place. So instead of having two protons forcing together, which do not want to be anywhere near each other, protons hate being stuck together. There's a lot of force required to hold them there. Suddenly one of them turns into a neutron. Now we have a proton and a neutron. And we have no requirement for all that energy anymore. And it is released. Okay? It gets more complicated than that because it's not going to happen once. It's going to keep happening. We're going to keep piling in more protons. So the next one, we've got two protons and a neutron. Again, the two protons don't want to be there. They're not stable. Okay? They need the nuclear force to hold them together. They don't like it. So again, we get another proton turned to a neutron. Another release of energy. In fact, we get to a point where we have two protons and two neutrons. What am I talking about? Two protons, two neutrons.
Oh, nuclear.
In the nucleus, if I have two protons and two neutrons, it's what we put in balloons and they float. Helium. In fact, our sun is about 20% helium as it's using fuel. So it's mostly hydrogen, and that's good because that's what hydrogen is fusing together. And as it fuses, it converts it to helium. So when the sun runs out of hydrogen, it's all helium, it ceases to be a sun. It will start to expand and then collapse on itself. Okay, so it's all a big process. Again, you're setting yourself up for a 6 marker there. If they ask any question about fission and fusion, just being able to draw a couple of circles and make sure you know the difference and the similarities, you're laughing. You're gonna put together a solid answer quite quickly without having to stress too much. Questions, queries, and doubtful points, guys. I've rattled through that. There was one I said I'd go back to if we had time. Can anyone remember what it was? I don't remember who asked it, and I can't spot it. Never mind, I'm sure it'll be covered in the other videos.
I think it was about cancer.
Oh, treating cancer. Oh, it's in the other video, so I won't go through it again because I'll bore people to tears if I do that. But I drew the world's worst diagram. Hopefully it makes some sense to you. We're up to 40 minutes on the video anyway, so I will sign off to those at home, and then I'll continue talking to you guys.